With that, let me turn it over to Helene Sear, who will be introducing our speakers today. Go ahead, Helene.
Thank you, Bob. Thank you, everyone, for joining us this afternoon, 2 p.m. Eastern Time. Today, we're going to look at where dedicated bioenergy crops should be grown. And this webinar is going to address land use change associated with production of bioenergy feedstock utilizing data from the billion-ton update that was done in 2011. And it's going to project spatially explicit potential availability of various bioenergy feedstocks and how this is influenced by price and other assumptions that Matt and Lawrence will be going over. To introduce our speakers today, Dr. Matthew Langholtz with Acreage National Laboratory. His primary research interests are in biomass resource economics, short rotation woody crops, and bioenergy from forest resources. He has worked on short rotation woody crop economics, valuation of non-market externalities, and developing biomass supply curves for the southeastern United States. His background includes agroforestry, extension, and work in Latin America with the U.S. Peace Corps, and production of herbaceous and woody cellulosic biomass crops in the South, in the Gulf, in southeastern United States. He has a BS in forestry from Oklahoma State University and a master's of forestry and a PhD in forest economics from the University of Florida. He's currently in the bioenergy program of the Environmental Sciences Division of Acreage National Lab in Acreage, Tennessee. The other speaker that I want to introduce is Lawrence Eaton. He is a research scientist in the Bioenergy Resource and Engineering Analysis Group at Acreage National Laboratory as well. He is trained as an economist and applies economic and GIS tools to energy and environmental research. He is actively involved in research to estimate biomass feedstock supply curves, land use change associated with energy crop development, energy price forecasting, and ecosystem valuation. He holds a BA in Economics and Environmental Studies from Washington and Lee University, and an MA in Economics from the University of Tennessee in Knoxville. So obviously there's going to be a lot of economics involved in today's discussion and pricing. And so I'm going to let the experts discuss what they're going to talk about today. So Matt, if you want to go ahead, I'm going to turn my mic off.
Sounds good. Good afternoon, everybody. Thank you very much for the introductions, Bob and Helene. I'm Matt Langholtz. I'm here with Lawrence Seaton, my colleague on the Resource Analysis Project here at Oak Ridge National Lab, where we work on resource analysis work for BETO, the Bioenergy Technology Office of the Department of Energy. And like Helene mentioned, we'll be looking at results from the billion-ton update that came out in 2011. So I suspect some of you might have seen our work in one form or another, might have seen the report. But I think this presentation it's actually an interesting opportunity for me because we've presented a lot on the billion-ton update. We've presented frequently on our results, on our supply results. But in my mind, we often kind of gloss over the land use change issues behind our results. So I think this is a neat opportunity to unpack that a little bit more and give it a little more consideration. And Lawrence, please feel free to interject at any time. So typically, when Lawrence presents this presentation, or when I present it, or when others at DOE present it, often about the first 20 minutes or so are about the modeling alone. And I didn't necessarily want to dedicate that much time to our modeling in this presentation. I'd be happy to go into it in more detail at any point with anyone. We can go there if needed, but let me just press on and maybe try to summarize that as much as possible. Basically, in 2005, this office came out with the billion-ton study which projected the availability of biomass supplies, but it begged the question, what sort of prices might be needed to incentivize production of the supplies that we were expecting to be potentially available. So that was kind of the impetus for the 2011 billion ton update, where we emphasized forecasting the economic availability of biomass supplies. In other words, not just how much can you get, but how much can you get at what price. How much would you have to pay for the supplies that you might need for biofuels, to support a biofuels industry. And we do that with an economic model called POLYSYS, or the Policy Analysis System. It's a linear program of the national U.S. agricultural sector. It runs nationally with optimization at the county level and solves for the most profitable allocation of agricultural lands to different types of production. And it includes, I definitely should emphasize that all of our work and many assumptions behind our modeling in the billion ton update come from many individuals across many institutions across the U.S. Too many to name in this short presentation, but I definitely need to acknowledge the collaboration from many individuals. Chances are many individuals on this call are contributing to our yield assumptions and our economic assumptions behind our modeling. But at any rate, with this model, we make 20-year projections of the economic availability of biomass feedstocks, supplies as a function of price, location under different scenarios. As you can see, we have a range of a variety. I'm trying to break out my little mouse here. There we go. A variety of forest resources, logging residues, thinnings, conventional wood, other types of forestry resources are included in the analysis. But on the POLYSYS side, POLYSYS runs on agricultural lands alone. So on the POLYSYS side, on the agricultural side, we include modeling of conventional crops, and to POLYSYS we have added cellulosic biomass feedstocks to include crop residues, perennial dedicated feedstocks, perennial woody crops, another type of dedicated feedstocks, and annual energy crops. So the four bolded categories that you see here are the ones that particularly could cause land use change as modeled in POLYSYS. And by the way, if there are any clarifying questions, please maybe chat those to Helene, and I'd be glad to clarify. So a little more on the POLYSYS Modeling Framework. Again, this national model that runs at the county level includes 8 major crops, including corn, soybeans, wheat, sorghum, oats, barley, rice, and cotton, as well as hay, hay, livestock, and food feed markets. It includes projected demands for food, feed, and industry and exports. And again, to this model, we've added potential biomass feedstocks in 2 broad categories. There are agricultural residues, including stover, straws, cereal straws, and energy crops, like I mentioned a moment ago. And I should emphasize that these dedicated biomass feedstocks are allowed only on agricultural land, and we do not simulate land use change between forest land and ag land. So we have forest resources and we have dedicated agricultural feedstocks, but in this simulation we don't allow, it is assumed that we don't produce what I'll call dedicated cellulosic feedstocks on forest land.
So Matt, quick question for you from FG Beauregard. Sorry if I pronounced that wrong. He's wondering, do the ag resources include ag conversion lands like CRP lands?
No, the assumption there is that there's like a no sunset policy, so that all the acres that were enrolled in the base year of analysis in 2009 would be extended throughout the projection period.
Perfect. Thank you.
They said they couldn't hear that, so if we could have that repeated, please.
Oh, yeah.
Yeah. The assumption, well, for CRP lands is that they remain enrolled. There's no more all crops that expire re-enroll. So the number of acres that are in CRP in the base year of analysis, which was 2009, would continue their enrollment in CRP throughout the projection period.
But we don't allow production of dedicated feedstocks on the CRP land.
That's right. We don't allow any change in that policy.
That's not to say it couldn't be done, but just in our conservative modeling, we don't produce dedicated feedstocks on the CRP land. But that's another very interesting question.
Yeah, great question.
Yeah. Does that work?
Yes, that works.
Okay. But we do simulate production, potentially, of these dedicated feedstocks on these agricultural land bases, including 250 million acres of cropland, 22 million acres of cropland pasture, 61 million acres of hay, and 181 acres of permanent pasture. And there are some more detailed assumptions on the pasture conversion. I should add that this is done in collaboration with the Agricultural Policy Analysis Center at UT, and there's more information on this modeling framework available in the billion ton update. So typically a presentation on the billion ton update goes through the next 30 minutes of different types of feedstocks that might be procured at different prices, but I'm going to give you the summary right up front and then unpack it a little bit within the context of land use allocation. So I mentioned the 2005 billion ton study where we estimated approximately 1 billion dry tons available under a moderate scenario, or potentially more under a high yield scenario. Under the 2011 update with our economic modeling with POLYSYS, while our more conservative assumptions on residue removal on the ag resources and our more conservative assumptions on logging residue retention constraints on the forest resources, while with the 2011 update we model slightly less forest residues and ag residues being available than we had in the billion ton update. With the inclusion of energy crops responding to markets, we have upwards of 1 billion tons modeled available assuming a farm gate price. So all this discussion will be at the farm gate. So assuming a farm gate price of $60 per dry ton by 2030, our simulations suggest we'd have upwards of 1 billion tons available at the farm gate under the baseline scenario, with much more potentially available under a more optimistic high yield scenario. More detail, basically the high yield scenario includes assumptions of more optimistic yield improvements. So looking at that in a little bit more detail under different prices. So part of the story is if you don't offer any prices, then probably no one is going to deliver anything. If you offer some feedstock prices, then you're going to get some feedstock. If you offer more, if you offer higher prices, then farmers are and landowners are going to produce more. So we get so if the y-axis is supply that's being produced, then as we offer higher prices, we get more supply, and as adoption increases over time, we also get more supply. And the black line indicates ESA targets, realizing 21 billion gallons per year by the year 2022. Basically at most prices, at least at a farm gate price of $50 a ton, our simulations suggest that under this baseline scenario, we would get more than enough feedstock. It looks like about the equivalent of about 35 billion gallons per year. That's more than the target of, so I should say enough feedstock supply to produce about 35 billion gallons a year, more than enough than would be needed to meet the ESA target of 21 billion gallons a year by 2022. And just to expand on that a little bit more, if this figure on the top was the same as the one that we saw on the previous slide, as the baseline scenario, this is just a high yield scenario, indicating that with more optimistic assumptions about yield improvements in the future, we potentially have the production of a lot more dedicated energy crops, and also potentially more land available for the production of those energy crops, as there are potentially yield enhancements with our conventional crops.
Matt, there's a clarifying question from I think it's Clyde, or Mr. Hamilton, I'm sorry. These projections out into the future, did you hold the climate at a steady projection? Did you influence any climate change as far as how many crops, or projected feedstocks availability? Is that held constant, like the weather?
That's a great question, and the answer is yes. It's assumed constant, and part of our peer review is to account for climate change projections in our feedstock price and supply projections, and we actually have a task to work on that this year. So that's a very interesting question.
Okay. All right, thank you.
Yeah,
comment from Lawrence.
Yeah, this is Lawrence. One point to make is that we're bringing over the assumptions from the USDA long-term baseline, which, like Max said, basically assumes there's no abnormal weather events. So there's basically the yield growth follows historical growth, which is about, like for corn, around 1 to 1.2% per year increase in the national average. And the high yield it varies between basically for corn would be up to 265 bushels per acre average in 2030. The baseline would be 210 bushels per acre national average in 2030.
Does that imply more conservative assumptions on yield improvements on the part of USDA projections, or what's the implication of that? Do you think?
It's just that. Yeah, I mean the USDA baseline forecast is that what it's basically an agency consensus report, and it's basically a reference scenario from which you can make alternative assumptions lower or higher than that. So it's not assumed pessimistic or optimistic. It's just assumed that really it's a reference case.
Yeah. I guess I would add, don't quote me on this, but with the discussions that I'm having in preparation for including climate change in our feedstock supply and price projections, if our projections are to 2017 and to 2022 and even so far out to 2030, the climate change models that I am being pointed to use to account for climate change in our supply and price projections, they don't show a whole lot of change in the time frame that we're talking about right here. So that's definitely very relevant, and it's an interesting question. I digress, but we're going to be looking at that this year. So I'll press on, unless there are any more questions on that. So this might be a good way to try to illustrate the sorts of information that we are producing with our modeling. And all this data this county level data on supplies and prices. The data are available at bioenergykdf.net, and we'll show that link a little bit later. But in short, so this little figure on the side here, these are supply curves where as you offer higher prices, potentially you get more supply. And they are different supply curves for different years and different scenarios. So for example, to start out, this scenario, these are results for a baseline scenario, results in 2022, at $60 a dry ton. So for example, at $60 a dry ton in 2022, under this scenario, you get about 200 million dry tons in that year. And if we take that same scenario out to 2017, then we see the supply curve here shifting out to the right, and we get about 327 million dry tons in 2017. But if we were looking at the high yield scenario at the same year and the same price, then we're talking about half a billion dry tons, about 500 million dry tons at the farm gate. And if we continue out to 2022, back to the baseline scenario, then we're talking at about 529 million dry tons. And if we go to the high yield scenario of 2022, again that same price, then we're talking about 850 million dry tons in 2022. I think that's the last one, yeah. So, and you can see graphically the kind of the expansion of cellulosic feedstock production over space and over time as these under these different scenarios, and expansion into the future potentially. So what I wanted to do was, as we see these different supplies as far as dry tons per year being available at the county level, I wanted to characterize a little bit those potential supplies. So here we're looking at the sorts, just the broadest categories of feedstocks that might be produced. For example, agricultural residues. Agricultural residues come from parts of the country, like the Corn Belt, where we're producing agricultural crops. Forest residues come from the southeast and the northeast and the west, where we have forest resources. And our energy crops are projected to largely come in the plain states. And our energy crops, so on the point of the energy crops, I'll go to the next slide, where we break those out by type a little bit. So here these are also categories of feedstocks showing the types of energy crops broadly, such as perennial grasses. Again, on the plain states, energy crops being largely comprised of perennial grasses. Woody crops having great potential in the south, in the southeast, in the northeast. In the lake states, I should say that woody crops in the northeast and the lake states are simulated as coppicing willow. And in the southeast, they're simulated as a non-coppicing 8-year rotation kind of generic species. Maybe it's pine, maybe it's poplar, maybe it's eucalyptus. And there's also some potential for annual energy crops, such as sorghum. Some discussion about the forest resources. A great potential for production of woody feedstocks in forested areas of the country, coming from different types of silvicultural operations. We have integrated operations, which is kind of a simulated silvicultural operation of combined collection of logging residues and piggybacking on that operation, a stand thinning. So we potentially have a lot of supplies coming from that sort of integrated forest operation. We have other removals, another FIA category, which is basically other types of wood that could come into supply during silvicultural, during harvesting operations. We have other forest land things potentially being available, so slightly less productive types of forest land. Mill residues are largely already used, but potentially there's some of that supply available. And a low-hanging fruit might be urban wood waste that's largely available from large municipal areas. And also, under certain price scenarios, some potential for, under certain market conditions, pulpwood being potentially available in the southeast for a bioenergy market. So maybe transitioning then, so after discussing those sorts of feedstocks that might be available under different prices, under different scenarios, I wanted to put in context the land use change associated with these projections. So POLYSYS is basically a land use change model. And at $60 a dry ton, the total land use change is estimated to be 63 million acres under the baseline scenario and 79 million acres under the high yield scenario by 2030. So here we basically see an increase in land allocation to dedicated feedstocks. So let's look into that in a little more detail. So so here we have different farm gate prices and different years. And what I might do is just focus on a most aggressive scenario, which, mind you, eventually produces, so for example, at $60 a ton, under the base case scenario, by 2030 we're producing about 1 billion tons of biomass, which is approximately 4 times the amount of biomass that would be needed to meet current ESA targets of 21 billion gallons a year by 2022 and staying flat after that. So we're talking about a very aggressive scenario, potentially producing enough second generation biofuels to displace 30% of our current petroleum use, which in my mind is very aggressive. But let's just look if we had a very aggressive scenario like that, what that would mean in terms of land use allocation. So if we look to 2030, if we combine the land allocation under this simulation, if we look at the land that's allocated in our results to perennial grasses, something like 43 million acres, plus land that might be allocated to woody crops, I just kind of eyeballed it, at something like 18 million acres, plus something for the annual energy crops. So all those combined, we're talking about approximately 60 million acres of land allocated, 60 million acres of agricultural land allocated to dedicated feedstocks. So there's additional feedstocks coming in the form of agricultural residues. There's additional feedstocks coming in the form of forest resources. But as far as agricultural land use change, we're talking about approximately 60 million acres. And just in round numbers, approximately half of this might be allocated to cropland, and approximately half of this might be allocated to pasture. But let's just think about it in terms of round numbers like that for the moment. So in context of the total agricultural land, currently we're looking at about 231 million acres, down from a high of 271 million acres. So if we're talking about, under this very aggressive scenario, producing 4 times the amount of biomass supply needed for ESA, we're talking about 30 million acres. I think that's about 13% of current agricultural land. It's something like 11% of agricultural land at its high in '82, and it's less than the approximately 40 million acres of the difference between the two. So it's not it's worth taking into consideration. It's worth taking into consideration. Let me leave it at that for now. And maybe with some discussion, try to put that amount in perspective. So again, under the baseline scenario of $60 ton farm gate price by 2030, we have over 1 billion dry tons produced, and with an assumption of about 85 biofuels yield of about 85 gallons per ton, that produces 85 billion gallons per year, or about 1/3 of current petroleum consumption, which again is 4 times the ESA target. It includes dedicated crops on up to 30 million acres of cropland and up to 50 million acres of pasture land, but not this maximum at both. So again, to reiterate, current cropland is 231 million acres. So this high of 30 million acres would be about 13% of that. I would add that current pasture is 460 million acres. So if we were to allocate 50 million acres to dedicated feedstock production, that would be about 11% of that total. With that, I'll hand it over to Lawrence to talk about land use allocation change.
Thanks, Matt. I was going to spend just a little bit of time so that we would have enough space to answer questions if needed. But what I wanted to just discuss on the final few slides is really, what are the deltas across these years and these prices that we're projecting out in the future. I think really one of the important things to point out is that, historically speaking, the amount of land allocated to traditional crops has decreased over the past 4 years, as Matt showed earlier, and also the baseline projection from 2009 also indicates that. So you see a reduction in corn and soybeans, a little increase in wheat out to 2030, and that's the extended baseline period. But really, the underlying driver behind this is that yield increases generally make up for make up demand. Again, there's a lot of things going on in markets, and it's hard to maybe come up with this conclusion if you see what's going on now with record plantings and also pretty optimistic yield assumptions. Underlying also this is rotations are changing, and the way we modeled it was because we took into account some pretty highly detailed estimates of sustainable stover removal. We had to assume away a lot of that, the resolution there. But to assume away a lot of historical rotations that really now is changing in 2013 based on when we did this analysis in 2011. But the point being here is breaking apart each of these categories and seeing how they're changing. Yes, you see reductions in traditional crops, but because of yield increases, you don't really see a lot being missed in the markets. The markets are still clearing, and all those demands are still satisfied in the market. So when you see $40, $50, and $60, like we were just focusing on the $60 mark, we do see reductions in corn, wheat, and soybeans, and increases on the highest in the highest point perennial grasses on cropland in 2017. Now in 2030, we see pastureland really making up the largest in this category of land use allocation. To talk a little bit more about residues, and that because this is sort of an interesting way that this is modeled. We talk about a baseline, and we talk about a high yield, and we also talk about a high no-till. And what high no-till allows is for not only a little bit bumping the yields, because that removal of the stover allows soil to warm up earlier in the season and allows farmers to get a little bit of a head start. It also provides more residue. It's from a higher ratio of that whole plant can be removed because the soil isn't disturbed. So what we're looking at here is allocation of crops into the different categories, and this is high no-till, acreage and no-till, and across the different price levels, 40, 50, and 60. So we have $40, $76, $50, it's the 75, the green, and then $60 at 74. And these are just some scenarios just to show how each of these sources is competing for land. So when you add a high yield for energy crops, you see a dip in the amount of corn acreage in no-till corn. Anyway, this is kind of detailed, maybe outside the scope of what we're talking about here, but wanted to point out that that there's some interactions in all the between the crops, and also in this case tillage regime. And back to kind of more, the subject we're talking about here, cropland to switchgrass, pasture to switchgrass, and then cropland to woody, and pastureland to woody. And these are just some sort of some paths for allocations projected out into the future across some different scenarios. A baseline, a high yield energy crop scenario, a high yield high no-till, and a high yield high no-till at 3%. And really what basically these y-axes are all the same, 30 million acres. You see cropland to switchgrass is a big category, but really pasture to switchgrass does dominate. This is all $50. Pasture to switchgrass dominates at 60, which is not included here. To a smaller degree, cropland to woody and pasture to woody. We show a significant portion of land converting in this simulation. And really to tie a bow on all of this, this is the final slide to put a plug out for the Bioenergy KDF. And what the Bioenergy KDF stands for is the Knowledge Discovery Framework. The URL is down here below. You can register for a free account and access all of the projections that we've used in this presentation for your own analysis down to the county level, whatever price and year and scenario you may be interested in, and actual feedstocks as well. What the KDF really is it's a website which you can access data and mapping tools, and there are actually a handful of models which you can interact with. The Billion-Ton Data Explorer is one where you can visualize on the fly your own custom supply scenario and identify areas where there might be higher amounts of resource that you may be considering for your project. And there's also there's a custom data download tool where you can basically download bits and pieces, more than just say one price, 1 year, one scenario. The custom data download tool allows you to sort of aggregate up. And the last is that there's all the data that you can extract on your own, download all of it, and summarize how you'd like. There's an API out there as well, which is Application Program Interface, for those of you maybe more tech savvy who don't want to host the data but still want to be able to use it. You can tap into our server and access the data there, all of that for yourself on the fly without having to host it. Basically, the tool workflow follows the organization of the report, which Matt alluded to in the first few slides for agricultural resources, forestry, and then also the waste resources. And basically, you can follow this sort of tool to choose what you're interested in, project that on the map, and actually in this third screenshot, you can actually go in and kind of really feel the data by down selecting and exporting data that you may be interested in. So what this does really for you is you see a supply curve, say up here, of corn stover in 2022, and go in through the workflow and actually project that out onto a map and see for yourself what the spatial distribution looks like. You know, connecting this with your own tools or your own assumptions, you can aggregate, you can manipulate the data however you'd like. But what this provides you really is access to millions of records and really a pretty robust collection of information for those of you who may be interested in facility siting or plant policy or actually you know, planning your own facility. So the Bioenergy KDF, again, the URL is below. This is the billion ton is sort of a future product on that web resource, but at the same time, there's a lot more available. Other models, other data sets, spatially oriented information, and also a pretty significant library on bioenergy and biomass resources. So I think with that, I'll hand it over back to Matt, and he'll wrap up the presentation.
Yeah, just really quickly, I felt like that was all really good. So I guess, you know, in summary, you know, we don't pretend to know exactly what the future holds, needless to say, but research suggests that there are a lot of different types of feedstocks potentially available with wide geographic distribution at $50 a dry ton. By 2022, we get more than enough supply than needed to meet our ESA targets. And by 2030, we could potentially displace about a third of our petroleum consumption. We're talking about a production of over 1 billion tons, displacing 30% of our fuels, might use about 10% of our cropland, about 10% of our pastureland. I did want to say a lot more discussion about this topic is available in section 5.3.3, land use change economic impacts in the billion ton update. Maybe I would just leave on this note, with the amount of land use change and increased demand that we're talking about, if you look at table 5.6 in our report, in 2022, under this baseline scenario, corn prices are expected to be $3.60 per bushel without feedstock demand. If we add this farm gate price of $50 a dry ton, then corn price increases 3% to $3.71. By the way, that's not an increase in the Big Mac index. That's just an increase in price of the farm gate. And if you're listening to NPR this week, you're hearing about demographics, aging demographics of farmers. And the flip side of that coin is that total agricultural net revenues would correspondingly increase from $180 billion in 2022 to $186 billion in 2022. So that's the other side of that coin. And with that, I will return it to you, Helene and Bob.
Thanks, Matt and Lawrence, for a great presentation. Did keep track of some of the questions that people put into the chat window earlier. And it goes back to your slide on the baseline scenario summary. You're projecting the allocations for energy crops and forest land. It kind of goes into the, I guess, what model you used on all your assumptions that you used. But one of the questions was, how does natural gas production affect these projections, especially with the need for energy? And you know, do you think policy is going to uphold all these projections, or do you think things may change?
I'll take a stab at that, and Lawrence, correct me if I'm wrong. But the way I see it, so what we simulate here are farm gate prices. So this is if you offer $40 at farm gate, this is what you get. If you offer $50 at farm gate, this is what you get, etc. So obviously, basically what cheap conventional fuels means is that it's harder for biofuels conversion industry to compete. It's harder for biofuels to offer $60 a ton. Maybe now they can only offer $40 a ton. So basically, it's just the old story. The way, in my view, it's the old story of cheap conventional energy, which is good, but it's not good if you're interested in renewable energy. As far as deployment of renewable energy, it makes the economic viability of renewable energy more difficult.
Same slide, another question. On the bottom slide, you have the 4% energy crop. And I guess the question was, do the 4% gains include physiological and other biological constraints to plant yields projecting into the future?
So that is based on the 2010 high yield workshops that were developed by, put together with, I think we're talking 50 or more experts in the room at that time, kind of deriving consensus on these different types of scenarios. Whether or not it includes physiological constraints, I think it does include physiological constraints. It also, basically that is designed, correct me if I'm wrong, but that's designed to illustrate potential yield improvements that could be achieved with some combination of genetic improvement, and improved management. Yeah, and Florence is nodding, so I think, hopefully that answers.
I don't see any other questions typed in the chat window, but I would like to open the floor for any questions if you want to type them in the chat window. It looks like we have another one for you, Matt and Lawrence.
Okay.
This person wants to know, did you show information on conversion of land use versus increasing yields on projections?
Could you maybe repeat that one more time? Conversion of land use conversion versus what?
Increasing yields on projections.
So if by that we mean increased yields of our conventional commodity crops, then basically under that high yield scenario, for example, of 4%, correct me again if I'm wrong, Lawrence, but if corn production improves, then you don't need as many corn acres and you have more acres potentially available for dedicated feedstocks, is how I interpret that. Lawrence again is nodding.
We didn't run just to piggyback on that, we didn't really run any scenarios where we restricted land use. We varied the land conversion constraints. We had, I don't have them in front of me, but we have an annual conversion. I think it's like, between 5 and 20% for the different types of lands. That could be cropland pasture, or land that's in permanent pasture. And then we had a cumulative constraint, which was 25% for all of the crops, some croplands, and for sorghum it was restricted to non-erodible land in a 3-year rotation with other crops. So it was a lot less than that. Sorghum was assumed to only grow on cropland. And for permanent pasture, the constraint is 50% of pasture in any given county would be available for production at the right, assuming it's the right price to outbid grazing. So that's a good question about varying those constraints. That was outside the scope of this report.
Thank you. And I think you did mention on one of the slides the land use change by energy crop. I'm not sure if this is what Todd was looking for, but you did have at the highest simulated price 22 to 30 million acres would be cropland, and approximately 40 to 50 million acres pasture. And correct me if I'm wrong, Todd, I'm not sure, and if you need some further clarification, just please go ahead and type that in the window. I'm not sure if this is what you're referring to or not.
I think the highest simulated price in the report was $60 a dry ton. I think the 22 to 30 referred to the baseline versus the highest high yield, which is 4%, and the 40 to 50 would be the baseline and the highest the high yield.
So 2 different scenarios, baseline scenario versus the high yield scenario.
You said thanks. So he got that question answered. I don't see any other questions, so I guess we're going to continue forward.
Okay, thank you very much.
Thank you, and I would like to thank, let me move the PowerPoint towards the end here. There we go. So there are some steps that you need to do to complete this webinar to receive your continuing education credits. And I'm going to let Bob explain that further. But I did want to mention that this webinar was supported by the Agriculture and Food Research Initiative Competitive Grant and the Renewable Resources Extension Act, both from USDA National Institute of Food and Agriculture. And thank you, Lawrence and Matt, for taking the time out this afternoon to give us this, or to provide this presentation. And just to mention that this presentation will be available on the Bioenergy portal's website, so you can download it further or share it amongst your friends. And I'd like to thank everybody for coming. And Bob, do you have anything else to say?
Thanks, Helene. Thanks, Matt. As Helene was pointing out, folks, we do appreciate all feedback that we can get on doing these webinars. I've put the link in the participant window. You can click on it there, but I'm also going to push it out through the system here for you to be able to follow. And what's going to happen is it will open up your browser and to the page, and it'll just take a little bit because 30 or so folks here are getting pushed out at once, so that window should pop up for you shortly, so just be patient. And as Helene pointed out, if you're interested and you're not already subscribed to the portal's email list, feel free to go to bioenergywebinars.net and click on subscribe, and that will give you the opportunity to subscribe to the email list and find out more about bioenergy webinars as well as other forestry related webinars. You can choose the different topics that you'd like to subscribe to. So with that, thank you.